Good morning, my name is Rui Matos and I'm here to present the work called Experimental and Numerical Analysis of Three-Point Bending Tests of Steel Beams with Web Holes. This presentation will be divided in the following points: some introduction about the objectives and focus of this study, Precambering experimental tests, description, layout and instrumentation, material characterization, experimental results, numerical model description and validation, and finally some conclusions. So this study will focus on filler beam decks, which are nothing more than composite solutions composed by a concrete slab. As you can see here in this picture in yellow, we have the concrete deck that are heavily reinforced in longitudinal direction with these hot rolled beams and also including some transversal rebar reinforcement that cross the webs of the hot rolled elements. So we see here the representation of the transversal rebars. What are the main advantages associated with this solution? So there is high corrosion protection because the steel hot rolled beam is embedded in the concrete, so there is correct corrosion protection needed only in the bottom flange. It's a robust, simple and durable solution with no need of highly specialized labor work. It's a solution with high load carrying capacity, and it's mainly used for decks with restricted construction depth, bridges crossing roads that are functioning, open roads, because the erection is both quick and easy, and also for replacing decks in existing structures. This is a solution with quite shallow slab thickness. And the spans are normally ranged between or around 40 meters for road bridges and 35 meters for railway bridges. So to accomplish these filler beam bridges, the precambering process is quite required, and basically this precambering process is a process to induce permanent deformation on the beams, normally a parabola shaped deformation, to compensate deflections due to permanent dead loads and also some part of live load. And this permanent deformation can be induced either by force application, the so-called cold cambering, or heat, so heat cambering. In this case of filler beams, as I mentioned before, some holes are required in the web for crossing of the transversal rebars. The execution of this cambering and this deformation will of course lead to some plastification of the section around the hole, which may lead to some undesired ovalization. This ovalization of course cannot extend forever, and we have some target values for this maximum ovalization, which in this case we did according to the recommendations from Eurocode from 10025 standard, and we considered a maximum deformation of 1 millimeter for class 1 structures and 0.5 millimeters for class 2 structures. In terms of experimental tests, so basically these experimental tests were done to try to understand the behavior of these elements with the web holes. And for this study of the behavior, 6 tests were carried out on 2 different sections, 3 tests per section, 3 tests on AGA 400 and 3 tests on AGB 600. Respectively, with 4 and 6 meters of span between supports. The hole spacing was kept constant as 150 millimeters, and the hole diameter was considered as 30 millimeters for the AGA 400 and 36 millimeters for AGB 600. In order, of course, to understand this behavior of the beams with the web holes, or Extensive instrumentation was used, like LVDTs, load cells, strain gauges, all of these, of course, with the objective of understanding this behavior or estimating this behavior. And also the deformation of the holes was estimating using this digital image correlation technique. This digital image correlation was applied only in the middle hole, in the mid-span of the beam. The material characterization was performed with coupon tests. These coupon tests were extracted from the specimens, and it gave us a result of S355 for the AGB 600 and S460 for the AGA 400. All the results are within the requirements from 10025 standard. The samples, also according to 10025, were extracted from the flanges of the elements. The average yield stress for the AGB 600 was 423 megapascals. We see it here in this representation of the curves. And for the AGA 400, we got a value of 513 of average. For the yield stress of the AGA 400. In terms of ultimate stress for the AGB 600, we got a value of 504 and 558 for the AGA 400. The failure in the case of this example is the results of test 1 in the one of the tests, the first test on the AGB 600. And we got a failure at 1,688 kilonewtons, corresponding to a bending moment at midspan of 2,532. And the failure mode observed was web buckling in the area of the holes. You see it here quite well, the final deformed shape of the system. As I mentioned, the digital image correlation was used to allow a comparison between the deformation of the holes and the applied force. And in this graph, we can do something like that. Let's imagine that we want a target maximum ovalization of 1 millimeter. We go to this graph. We check where 1 millimeter was achieved. And for the same step, we go to the force graph and we take the correspondent force. For instance, in this case, we got a force of 1,667 kilonewtons of maximum force, or force for the maximum ovalization. Also, one good conclusion from the test, or one good observation, was that all the results were very similar from test to test. Here in this picture, we have in this graph and in this table, we have the results on all the 3 tests done on the AGB 600. We can see that the curves are all very similar, and also the maximum loading, the maximum displacement, everything is very similar, as you can see in the table attached. The same conclusions and the same observation was made for the AGA 400. We see here all the results of the 3 tests of the AGA 400, and all the results are very similar for all of them. Moreover, after this experimental study was conducted, some numerical model was developed with Abacus in order to mimic as much as possible the results from the experimental results. This model was done, what I'm going to present here is, let's say, the first approach to this numerical modeling, and this model was done with C3D8R, and which are solid elements from Abacus, and the number of elements was tested and implemented to avoid effects of shear locking and hourglass effects. And obviously the material introduced was true stress, true strain. Basically what we did, and as you know very well, we have here the expressions that correlate the engineering stress and the true stress and true strain. And basically what we got, we converted the curves from the coupon tests that I presented you before. we converted them into true stress, true strain, which we have here the values in dotted lines. And this is the curve that was implemented in Abacus. And also, in order to solve the problem, a Gminia analysis was considered, and the geometrical imperfections that were considered were equivalent to the relevant buckling mode shape. What we got in the end of this numerical modeling was quite a good agreement between the model and the experimental results, especially in terms of force displacement behavior. We have here in this graph the comparison between the model and the tests. The model is the dashed lines, the tests is the full lines, the 3 full lines, and the approximation is quite good. And also we see here on this image that the final deformed shape is quite similar with web buckling in the area of the holes as the shape that I showed you before in the pictures in the previous slides. In terms of conclusions, as you understood, some experimental tests were conducted to understand the behavior of these filler beams with web holes, and under Precambering loading, which was basically a 3-point bending test, and 3 tests were done on AGA 400 sections, and 3 tests were done on AGB 600 sections. The hole deformation was measured using this digital image correlation technique. The reliability was very well observed in the results. We got very similar behavior and resistance for all the specimens of each sections. Some preliminary numerical model was also done, some preliminary numerical modeling, and a good agreement was obtained between the experimental results and the numerical results, especially in terms of force displacement behavior and in terms of deformed shape. This is what I had for you. Thanks a lot for your presence and your interest, and enjoy the rest of the conference.